bulk model, bulk enhancement MOSFET, classic small signal transconductance model. Here non-linear operating point, small signal increments only, linear equivalent circuit, analog circuits biased through current sources, OPS function of drain current. This transistor, gate, drain, base, source. In between this drain and source, VDS not. Here base, in between base and source, VBS so S not. Here ID not, this direction current, drain current. Here VGS, gate to source. This is explaining this equation, non-linear operating point. This equation explaining linear equivalent circuit. And then in small signal increments only, VGS equal to VGSO plus VGS. This is VGS. So total, this VGS not equal to VGS. This is the small signal equivalent circuit, linear equivalent circuit. And then here VDS, here VDSO, here PDS. VDS in between VDS. There is, it is not showing VDS. Okay, VDS so then VDS. We will get it. We will get it from that. That will question. Then VPS, base to source voltage. VPS will not. Then VPS will get by VPS 0. Then VD. Yes. Sorry. Here no. VPS. This one. And then ID equal to ID not plus ID. Sorry. Then we will get capital AD. Small signal increments only. This one. Okay. Here is equivalent circuit. Here gate, base, drain, source. That is equivalent circuit. No. Here drain, gate, base, source. Okay. In between gate and base, gate and base, that is in between this. Start VGS. G, sorry, here is separate. Here is separate. Here is separate. Okay. So in between, here we can say yes. In between VGS, VGS, VG, yes. Then here gate plus minus. Here base minus plus. In between source and this is source. Source and B, VBS. Source and B and S. B and S here. Okay. GM VGS. Here GM VGS. VGS GM. Then conductance. RDS. Train in between train and source. Train and source here. Train and source. Train and source. This way. This is train and source. This resistance. Okay. That one RDS. RDS equal to 1 by GDS. And then GM VGS VPS here. This VPS here. Here VGS here. That is here. Both the GM. Okay. And then but here the GMP measuring, here only GM. And then here this linear circuit GM equal to this GM. This is actually where is happening. GS. Okay, no? GS. GM VGS in between here. What is happening? So, GM, this GM individual, what? Dou ID. ID, how much change? Depends upon with reference VGS. Here depends upon here will change. ID, here ID, VGS, that is VGS equal to VDS equal to VBS VBS 0. And then here, sorry, this ID VGS divided by VDS. VDS equal to VBS equal to 0. VDS, this VBS and the VDS here VDS, this is VBS, all are 0, 0, 0. Okay. So GM equal to this is. So here GDS equal to dou ID dou ID, that is not this is actually this is, because ID equal to ID not plus ID, no, ID and then dou VDS that is in between this one approximately equal to ID divided by VDS 0, VGS all are 0. Okay. So same here. So GMP ID by VBS, GM ID by VGS. This is GM ID by VGS. Next here GDS equal to ID divided by VDS. This is 0. Okay. Then VDS is less than or greater than to VD saturation. Condition GM, this GM approximately beta VDS. While VDS is more, VDS is between this, VDS is more here approximately, no, accurately this one, because VDS equal to VDS not plus VDS, small VDS. Okay. Then in here beta into VGS gate to source voltage, this voltage we have to multiply and then subtract VTH, because after VTH only it will start, no, that's why yesterday last video we have seen, equal to root of 2 beta ID, that is beta value ID value, then multiply with the 2, then take root square, because reducing that value. Scaling, we can tell this one square, root, all are scaling purpose only.